Okay, so what we are going to study today, that is the lecture number 7, and we will study about the stress and strain, and we will see how to measure and analyze the stress and strains in different parts of the machine or any structure. Okay, so before going to the measurement part, we will quickly recap about the fundamentals of stress and strain. Okay, so the definitions and some formulas, so that because you study the concepts of stress and strain maybe in your undergrad, or some of you may be studying it in masters also, but I think in order to make it more convenient for most of you guys, it's better to have a quick overview about stress and strain. Okay, so we will start with the introduction of the topic, and we will start with the definition of stress. So what is stress? Stress is basically the force per unit area, right? Force applied per unit area. And what about strain? Strain is measure of the deformation of material due to the stress. So if you apply a stress on a particular material, what will happen? The material will deform. Okay, so that stress can be on anything. It can be a structure, it can be a structural member, it can be any machine part, it can be any link of a mechanism, it can be anything. Okay, so if an external load or force or dynamic load or dynamic force is applied on some machine part or structural member, what will happen? There will be deformation, there will be deflections, there will be deformations. So there are two types of deformations which can occur when a stress is applied on a particular material. So if the level of stress is very much less than the yield strength of the material, what will happen? The deformation will be elastic. It means as soon as you remove the force of stress, the material or the structure or the part will return to its original shape. That is the elastic deformation. We have another type of deformation which is known as plastic deformation. So that in the plastic deformation, the force is very much, or the stress is very much higher as compared to the yield strength of the material. And due to that high stress, the material deforms, but that deformation is permanent, because now the deformation is beyond the elastic limit. And when the stress is removed, the material will not return to its original shape and size and dimensions. Okay, so that deformation is known as the plastic deformation. So whenever we work with different machines which have moving parts, we never want the parts to be plastically deformed. Okay, so because if the parts are plastically deformed, they will not be able to work the way they should work. Okay, so the working of the machine will be compromised, and we will not be able to get the work or the useful work which the machine was supposed to be doing. Okay, we can allow some sort of, or some intensity of elastic deformation. Okay, but if that elastic deformation is also beyond a certain point, it can affect the working of the machine. Okay, so the main thing is that the main function is that we need to limit the deformation or deflection of different members. Okay, but when we go to the strain gauges, so that is something else. But right now we are discussing the stress and strain, and we are discussing it with respect to the materials and structures. Okay, so this is what this epsilon A is. What that is? Axial strain, right? Axial strain, the strain which is acting, the deformation which is acting along the axis along which the stress is applied, that is the axial strain, and that is denoted by epsilon A, and that is equal to what? Change in the length divided by the original length. So what we have in this expression, we have epsilon A, which is axial strain, then we have L1, which is the initial dimension, initial linear dimension, or it is also known as the gauge length, or you can say that its initial length, that's it, L1. Then we have L2, that is the final length after the deformation. And which thing causes that deformation? It is the applied stress. So the stress is applied on the material, and due to the application of that stress, the length of the material or a part is now changed from L1 to L2. So if we take the difference of L2 and L1, what we will get? We will get the change in length. And if we divide the change in length with the original length, we will get the axial strain. Okay, what else we have? Okay, so let's look at this one. Let's say this is a member or a structure member or a part under concentration. This is a cylindrical shape part, and it has a diameter d1. Okay, this is one dimension. Then it has a length L1, and we applied a stress P. So what kind of stress is this? How many kind of stresses do we have? And what kind of stress is this stress P? Okay, let me just give you some hints. We have three kind of stresses. Okay, the tensile stress, compressive stress, or shear stress. So what kind of stress is this one? Okay, so this is the tensile stress, which is applied on a cylindrical component or part, and it has two dimensions. One is the diameter and the other one is the length. Okay, so when we apply this stress, what will happen? Its dimensions will be changed. So it has two main dimensions, and both of those dimensions are now changed. L1 is changed to L2, the length is changed from L1 to L2, and the diameter is changed from D1 to D2. Okay, so this was the actual shape before the application of the stress, and this is the shape of the cylindrical member after the application of the force. Okay, so now we can calculate the axial strain. Axial strain is what? Which is along the axis of the application of the stress. So that will be L2 minus L1, because the length is changing due to that applied stress. So axial strain will be L2 minus L1 over L1, and there's lateral strain as well, and that will be equal to what? That will be equal to D2 minus D1. D2 is the final diameter of the cylinder. So this one is axial strain and this one is lateral strain. Okay, that's good. Okay, so what will happen? One of those strains will be negative. Can you please tell me which of those strains, axial or lateral, will be negative and why? Lateral will be negative because the value of D2 is less than the value of D1. You can see that the value of D1 is greater as compared to the value of D2. So when we subtract D1 from D2, what we will get? We will get a negative value. Okay, so these are axial and lateral strains. Okay, the strain is commonly multiplied by 1 million because the strain is not that much. We generally get the strain in fractions. So what we do, we multiply it with a factor of 1 million so that we can easily calculate or use the value of strain in our calculations. Okay, so what we do, we actually use the term microstrain instead of strain. After multiplying it with 1 million, we call it microstrain. Okay, so we multiply that factor with 1 million and then put the micro here. So the effect of that 1 million factor is now cancelled. And we can also call a part per million. Okay, so now we will see what is the relationship between the stress and strain and how we can relate these two parameters. So if we want to relate stress and strain, then we need to introduce a constant which is a material property, and that constant is known as Young's modulus. Okay, or elastic modulus. So the elastic modulus is equal to what? That is equal to the ratio of axial stress over axial strain. Okay, so that capital E is a material property which remained constant generally, but there are there are few factors which can affect this Young modulus, like temperature. I believe temperature is a property which can change the Young modulus of a particular material. Okay, so Young modulus is equal to stress over strain. So we have epsilon A, which is axial strain, and we have sigma A, which is axial stress. Okay, so there's another relation which actually relates axial strain with the lateral strain, and that is the Poisson's ratio. Poisson's ratio is equal to negative of epsilon L over epsilon A, where this nu is Poisson's ratio. This is once again a material property. Then we have epsilon A, which is axial strain, and we have epsilon L, which is lateral strain. So why we put this negative sign? What is the purpose of putting this negative sign? Yes, because Poisson's ratio is a ratio and we don't want that ratio to be negative. So this fraction is negative value. This fraction is going to give you the negative value. So we need to multiply this with the negative sign so that we get the value of Poisson's ratio as a positive integer. Okay, not integer, positive value. It can be in decimals also. Okay, so if you don't have the value of Poisson's ratio, then the idealistic assumption is that you put the value of 0.3. Okay, so most of the materials have the Poisson's ratio in the range of 0.3. That is the average Poisson's ratio value. So if you are not given with the value of Poisson's ratio in any question, then you can assume the value of 0.3. If I put 0.3 here, what is the significance of that 0.3? How it relates the axial and lateral strain? Yes, lateral is basically 0.3 times of axial strain. Okay, so that's it. So we can go forward. Okay, so now we have another example in which we have a rectangular shaped object, and we are talking about this object in 2D. That object is placed in a plane, and there are two types of stresses applied on this object. One in the x direction, the other one is in the y direction. Both of these stresses are tensile stresses. It means they are stretching the material. So both of these stresses will try to stretch the material. Okay, so in order to calculate the strain, or in order to calculate the value of these stresses, what we will do, we will apply one stress at a time, and then we will try to calculate or try to formulate different values. Okay, so now what we are doing, we are applying sigma x to this member. So what will happen, this member will elongate along the axis, okay, along the direction of the axial stress. So it was like this initially, but when we apply the sigma x, which is a stress, what will happen? It will be deformed. It will be changed into this shape. So this is a deformation. It can be elastic deformation, it can be plastic deformation, depending upon the material and depending upon the magnitude of this deformation. Okay, so this was the original, the blue one is the original material before the application of the stress sigma x, and this yellow dotted rectangle is basically after the application of sigma x. So what we can do, we can calculate the axial and lateral strains. Okay, so can you tell me, is it axial or lateral strain? Axial. Axial, yes, you're right, because it is along the direction of the application of the stress. So this is axial strain. Okay, what about this one? This is lateral strain. Okay, this is perpendicular, in the perpendicular direction compared to the direction of the applied stress. So how we can calculate this one? We know that Young modulus is equal to what? Is equal to stress over strain. So if we want to calculate the stress, what we can do? We can simply get the stress by dividing the we can simply get the strain by dividing the stress with the Young modulus. This is what? This is the axial strain. So if we multiply the axial strain with the Poisson's ratio, what we get? We get the lateral strain. So this is the lateral strain, this is the axial strain. Okay, that's good. So now this is the deformed material. This is the deformed member or uh, deformed structure. Okay, that is after the application of sigma x. So now we still have one stress left, which is sigma y, and we need to apply that stress. So now we apply sigma y, and what will happen? The material or the structure will deform once again, like this. Okay, so now this is the final shape of the material after the application of two stresses. So now what we will do, we will compare what happened. So this is the original shape, the blue one. This yellow one is actually the shape which we get when we apply sigma x, and then we apply the sigma y on this yellow shape, on the deformed shape, and what we get this orange shape, and that is the final shape which we are getting. Okay, so now we are comparing this orange rectangle with the yellow rectangle. Okay, and what we will do, we will calculate, or we will try to formulate the expression for axial strain and what, lateral strain. Okay, so can you please tell me, is it axial strain or lateral strain? This is axial because this is along the, it's in the same direction in which the stress is applied. Okay, and what about this one? This is the lateral strain. So if we multiply the axial strain with the Poisson's ratio, what we get? We get the lateral strain. Okay, so now these values are with respect to the intermediate shape or intermediate form of the material. Okay, so now we need to see how much material is deformed in x direction and in y direction compared to the original one. Okay, so this is with respect to the intermediate state of the material or the member or the part. Okay, so now what we will do, we will compare it with the, we will compare the final shape with the original shape. So this is the strain in the x direction and this is strain in the y direction, and we need to calculate the values. So what we have in the x direction, we have two strains. One was sigma x over e, which was due to the application of the stress sigma e, and we have another one which is this one, and that was due to the application of sigma y. This was the axial stress, this was the axial strain, sorry, and this was the lateral strain. This was the axial strain due to sigma x, and this was the lateral strain due to sigma y. Why we put the negative sign? Because this term is smaller as compared to this one. So this is what we actually needed to calculate, this thing, right? We need to calculate this distance. So in order to calculate this distance, what we need to do? We need to subtract this distance from the distance between this surface and this surface. So what we do, we use this one. Okay, so in this way we can calculate the strain in the x direction. So it's the same thing, sigma x over e minus nu sigma y over e. Okay, so now what we do, we just take that e common, and this is expression for epsilon x. In the same way, we can calculate epsilon y, which is the net deformation in the y direction, and that is once again the difference between the deformation due to sigma y and sigma x. Why we put sigma y here? Because that is the axial strain. Axial strain is always greater as compared to the lateral. So that's why in y direction, sigma y is producing the axial strain and sigma y is producing the lateral strain. So that's why we subtracted this lateral strain from the axial strain. Same is the case here. Okay. So in this way we can calculate what? Epsilon y, which is sigma y minus nu sigma x over e. Okay, so with the help of these two equations, what we can do, if we solve these equations, if we solve these two equations simultaneously, what we can get? We can get the expression of sigma x and sigma y. Okay, so if we solve these equations, what we will get? We will get the expression of sigma x, and that will be equal to what? Young modulus multiplied by epsilon x plus nu epsilon y over 1 minus nu square. In the same way, we can get the expression for sigma y, and that is equal to Young modulus multiplied by epsilon y plus nu epsilon x over 1 minus nu square. What else we have? Okay, so now we are looking at a system or a part which is a 3D part. In the previous example, we have we considered a 2D part. There were stresses applied on that part in two axes, x and y. And now we have a 3D part, and there is a third tensile stress which is acting on the material or the member or the part of a machine, and that is the sigma z, and it is along the z axis. Okay, so if we have a system like this, what will happen? We will have three strains now, one in the x direction, the other one in the y, and the third one in the z direction. And these are the expressions for calculating the three components or three strains. Okay, so this x strain will be equal to sigma x minus nu sigma y plus sigma z over e. In the same way, we have sigma y, which will be equal to sigma y minus nu sigma z plus sigma x over e, and we have the third component, which is sigma z is equal to epsilon z, which is equal to sigma z minus nu into the sum of sigma x and sigma y divided by e.